There was a request by a couple of my AP students to talk about some topics, and we decided that it would be a nice thing to talk about maybe around one topic a week. And this week's topic is angular momentum. Angular momentum. Rotational dynamics is also listed on this slide. That is what's coming up next. So in the next episode, we will do the rotational dynamics. Okay, so when we're talking about angular momentum, before we get there, I'd like to first clarify a few terms. When we say an object is translating or when it's moving in a line, that is when every part of an object moves in a certain direction the same amount. Okay, so if something moves in a certain direction the same amount and every other piece of that object also moves the same distance in the same direction, the same amount, then we could say that object is translating. When we say an object is rotating, what we mean to say is that an object is turning or spinning around a point. Okay, so now let's look at these situations. Below we have a bunch of pairs of baseball bats, and let's take a look at each pair and think about what's happening in each of these pairs. Over here, you have two baseball bats, and you can see that this baseball bat has rotated to become this vertical one, right? Or you could think of it the other way around. It really doesn't matter. However, when we're talking about rotation, you always want to think about which point the object is rotating around. What is the center of rotation? And you can see here, excuse me, and in this example, the baseball bats are rotating around this central point, roughly in the middle of the two bats. And so you can imagine that the bat would rotate like this around this point in the middle, and that would be a rotation. Same thing here for these two bats, only this bat is rotating around a point at the bottom of the two bats. So again, it is rotating, it's turning. For example, this part does not move, and this part moves quite a bit, and so that would make this a rotation. These two bats over here, you can see that every piece of this bat has moved up, and it's moved up the same amount. So we can say very easily this bat has not rotated. The bat is still in the same orientation. The pieces are still oriented relative to each other in the same way. But since every piece has moved the same amount, we could say that these bats have translated. And this last one here is a tricky example, and this illustrates why it's important when you're talking about rotation to think about the point that the rotation is happening around. You could say with these two bats that the rotation is happening around this point right here. In other words, this bat right here, if you rotate it around this point over here, would give you this one eventually, if you rotated it like this from here to here. However, if you define the center of rotation to be somewhere else, we would notice something different happened. For example, if this were the center of rotation, roughly in the middle of the bat here, you could imagine straightening out this bat in place to make it vertical. And then once it was vertical, we could imagine translating that bat over. I guess since my camera is mirrored, it would be this way. And so depending on what you set as your point of rotation, these two bats could be listed as either a translation or either just a pure rotation or a rotation and then a translation. And you'll find that actually a lot of these examples can be listed as combinations of both of those things. Okay. Now, again, we're going to talk about angular momentum, but it's always a good idea whenever we talk about angular or rotational frames of reference to think about the linear version first, just to make sure we have a good foundation so that we can shift into the angular or the rotational stuff. When we talk about linear momentum, we're talking about the product of an object's mass and its velocity. It's roughly a measure of how much push an object has or how much force it can apply when it contacts another object. And this linear momentum is an important quantity to measure because when an object interacts with another object, or when we have a system of objects, we can group those objects together and look at the forces that are happening between those two as internal forces. And so the benefit of that is that when we're talking about linear momentum, the linear momentum of a system is conserved when no external forces apply. The linear momentum of a system of objects is conserved when no external forces apply. This is a super important concept to understand, and the if statement, if no external forces apply, is just as important as remembering that linear momentum is conserved. All right, so again, when we're talking about linear momentum, you should keep in mind that I mentioned that it is conserved for a system. The linear momentum is conserved for a system of objects. And it's really important when you're looking at the momentum of an object or set of objects that you're identifying what your system is. What am I talking about? Okay, so let me illustrate why this is important. You have a tennis ball. It goes from here to here to here to here to here. It's bouncing off the ground, and it contacts the ground, squishes, and then pushes back off, and then goes up into the air. Now, you should be able to see for this tennis ball the momentum, or let me ask you this first. For this tennis ball, does the momentum change? Okay. You should be able to say, yes, the momentum does change. The mass of the tennis ball is not changing. But on the other hand, the velocity of the tennis ball is changing. It's going down beforehand. It's roughly stationary in this part. And then in this part of the video, it's going up. And so because the velocity has changed from going down to going up, we can say that the linear momentum of this tennis ball is changing. It is not conserved. On the other hand, it's not conserved because there's an outside force acting on it. It's a force from the table. So if we were to look at, and the table is attached to the Earth is absorbing some of that impact as well. So if we say, let's take not the tennis ball, but let's take the tennis ball, tabletop, Earth system. And if we look at all of it together, then you can see that all these forces that are happening in this collision are taking place inside our system. And so from that frame of reference, we could say that the linear momentum of this system, the system including the tennis ball and the tabletop and the Earth, is conserved. Okay. Again, I just want to repeat that it's very important we understand that we have to ask the question, what object or group of objects are we looking at the momentum for? Because we can't apply the conservation of momentum principle unless no outside forces are applied. Okay. Momentum has a mass in it. Linear momentum has, or translational momentum has a mass associated with it. And that mass is a measure of an object's resistance to linear motion. As we've seen, a lot of these rotational concepts have the same idea in a rotational frame of reference. And for mass, its rotational analog would be the moment of inertia. If the mass of an object is its object or its tendency to resist linear motion, the moment of inertia of an object is a measure of an object's resistance to rotation around a point. Please keep in mind that which point an object is rotating around is very important because that drastically affects how easy it is to rotate an object. For example, if you had this heavy, like say bowling ball here, and you were to spin the bowling ball in place along this purple line around this purple dot, then you would roughly imagine it would be considerably easier than if you were to take the same bowling ball, hold it out maybe to the side with your arm, and then rotated it over your head like this. That is significantly more difficult. Again, because the point that you're rotating around is farther away from the mass that you are rotating. Please keep in mind that the moment of inertia is never innate for an object. It's only innate for an object around a specified point. And so again, when we're talking about rotation, you always want to keep in mind the point that it is rotating around. Generally speaking, a moment of inertia has a pattern that looks kind of like this. It is m times r squared. Many objects, many solid objects that are not, say, point masses, may have a moment of inertia that's going to be some sort of coefficient times mr squared. So a disk would be 1/2 mr squared. You have like a sphere, which I think is 4/9 mr squared, and various other fractions and things. But in general, you can expect that the moment of inertia of a mass is going to follow some sort of something times mr squared pattern. Okay. If you're an AP1, please take a look at this question, see if you can solve it. If you're an APC, please take a look at this one, see if you can solve it. It's good to practice these things. If you're unsure on moment of inertia or you just want some review, it's a good thing to practice here. It's worth mentioning that APC, we will be calculating the moment of inertia of this object considering that it's a disk instead of assuming that it's a point mass. And we'll get a slightly different moment of inertia for it, but it's going to be still largely very close to each other. Okay, so pause the video here, take a shot at it, and we'll resume in just a couple of seconds. Okay, The second thing that, okay, so let's see, we'll take a look here. You can see that if you just assume that the disk is a point mass, so we do mr squared right here, you can calculate the moment of inertia is around 20 kilogram meters squared. And if you were to be a little bit more rigorous with it and calculate the moment of inertia of this as a disk, and then say, oh, we're not rotating around the center of the disk, we're rotating around this point here, we'll get around 21 kilogram meters squared. So again, it's quite easy to get close enough just by estimating as a point mass, depending on which point it's rotating around. Okay. Now that we've established what the angular version of mass is, it's very easy to understand this formula of angular momentum. The angular momentum variable that we use is L, and we know that the angular momentum is equal to the moment of inertia times the angular velocity. And so what we can see here is that this is basically the angular or the rotational version of mass, and this is the version, same thing for velocity. So this is just momentum equals mass times velocity, but only written in angular terms. As you guys know, you can also relate the angular version of something to its linear version. And so we can say the angular momentum is equal to r times the momentum of an object. What I mean by that is if you know the momentum of an object traveling in a line, and you know the distance it is away from that point, then you can calculate the angular momentum of that object around that point. Let's draw that this way. Let's do it like this. Here is an object traveling in a line. And let's consider the rotation of this object around this point right here. So again, just to clarify, we have an object moving in a line, and it's rotating around this point right here. Okay, let's just give you the momentum up ahead of time. So let's say the momentum is 10, the linear momentum is 10 kilogram meters per second. And let's say this object is 2 meters away from the point that it's rotating around. Okay, so now we can calculate the angular momentum of this object by multiplying 2 by 10 and then taking the, let's draw an arc in here somehow. And calculating the cosine of this angle, roughly speaking. Sorry for the terrible looking drawing. I forgot to do this on the slide. Okay, so if we take 2 times 10 and then multiply it by the angle, the sine of the angle here, then that will give us the angular velocity, or the angular momentum. And it's important to remember that the angular momentum is dependent on these two things essentially being perpendicular to each other. So what you're doing here with the sine of theta is you're basically saying, okay, I don't want just the distance between the point of rotation and the object. I want to calculate the perpendicular distance, or how far it is away in a perpendicular direction from here. Okay. Next thing that we can do is we can think about calculating the angular momentum of this object around its center. For this one, you may find it easier to use this right here, I omega. Okay, so I've given you the moment of inertia of a disk, which is 1/2 mr squared. That will help you calculate I, and you should